This is oil. Thick, sticky crude oil. Black, dirty and unrefined. It's got a long way to go before it becomes fuel and lubricants, candle wax and chemicals. It has, in fact, 700 miles to go, from the wells in Upper Assam to refineries in North India. Only a pipeline can make economic sense of such a journey. So the sticky mess must somehow be persuaded to flow freely down 700 miles of pipe through little peasant holdings, which are the livelihood of small families, and great commercial tea gardens that are an important part of the economy. The wells and the refineries are both within the huge subcontinental state of India. And whilst agriculture is important, oil fuel supplies that do not have to be imported are precious beyond price in a land that's straining every fibre to become a self-supporting, modern industrial state. This is the upper part of the Indian subcontinent, with Assam on the right, and the barrier of the Himalayas at the top, and the route of the projected pipeline tracing itself slowly along from the oil fields, past formidable natural, economic, and political hazards to the refineries. Pumping stations boost the flow of crude oil at intervals. Very special pumping stations, for there is no fuel available along the pipeline save the crude, muddy oil flowing through it. The usual way of starting a big engineering project is to advertise the job in the press and let people who understand the work tender for it. In this case, the paper was the London Times, a copy of which was delivered as usual at the offices of W.H. Allen, Sons and Company of Bedford in England, who understand diesel and electric power very thoroughly indeed.
Please take a letter to the Burma Oil Company Pipelines Limited, Britannic House, Finsbury Circus, London EC2. Dear Sirs, Indian Pipeline Project, Diesel Generating Plant. Paragraph. We have read with interest your advertisement in the London Times and would be glad to receive the necessary documents to enable us to prepare and submit a formal tender. Yours faithfully, for W.H. Allen, Sons and Company Limited.
This scale working model of an engine was made by the apprentices at W.H. Allen's in their own training school. For any firm which intends to keep abreast of the fierce technical competition in modern industry cannot rely on chance for its supply of trained and expert personnel. And these boys may become the heads of departments who, not so many years ahead, may be making the same sort of decisions for the firm that are now being discussed by the chief designer and the manager of the diesel department. Once the specifications have arrived, the various design teams have to assess the difficulties, decide whether tried and conventional equipment will do the job, or whether special modifications or even entirely new designs may be called for. In the case of the diesel engines to power the pumps and electric generators along the North India pipeline, the biggest problem was fuel, for only the crude in the pipeline or natural gas from the wells was readily available, and the specification called for an engine which could use either at the turn of a switch. This was nothing very new in engineering, but the crude from the Nahokatia wells was a problem, as its high wax content makes it physically intractable and its low flash point requires respectful handling. Probably at no point in design more than now during the pre-tender work does that indispensable but unassessable quality of specialist experience play a greater part, because it's at this stage the fundamental assumptions must be made and decisions taken which will have to be turned into successful engineering and viable economics when the contract is placed. That's why every tender has the full attention of the best brains from the word go, and why there's no room at all for bluff, which would be called without remorse by the very forces of nature which it is the engineer's job to harness. The same quality of concentration on the work of tendering is applied to every inquiry, despite the fact that only a proportion result in orders. In this case, the particular solution of the engineering problems involved enabled an order to be obtained in the face of world competition. The arrival of heavy hardware from subcontractors is the visible evidence of the beginning of production, adding, as it were, a new ground base to the everyday racket of the machine shops. From an early stage of manufacture, testing is constantly carried out. Here, a cylinder liner is being tested well in excess of its normal working pressure. And here a technician is satisfying himself as to the parallelism and diameter of a crankshaft. Inspection and checking generally fall into two classes: control of manufacturing quality and accuracy, and the inspection of parts and indeed whole machines after test running under actual working conditions. To do this, the whole unit must be assembled and run, and before proceeding to this, it would be as well to take a look at the system of supplying fuel to one of the engines, remembering that this fuel is thick, crude oil. First of all, we have two conical bottom tanks, each holding 1 day's supply of oil and fitted with tubular hot water heaters to improve the viscosity of the oil by raising its temperature to about 100 degrees Fahrenheit. In order further to purify the now warm and therefore more tractable but still very dirty fuel, the sludge is allowed to collect in the conical bottom and drained away. The settled fuel is drawn from the tank in use by a circulating pump in a ring main system round each pumping station. It's passed through the main filter, then circulated in the ring main. Pressure in the system is controlled by a regulating valve at a normal working level of 10 pounds per square inch. The cycle is continuous, in that surplus oil is returned to the tank, then recirculated in the ring main, which is insulated to reduce heat losses. When the engines are running, oil is constantly being drawn from the ring main system by the fuel injection pump at a rate less than that at which the oil is circulating, thus ensuring that a reasonable flow is always maintained in the system. That was a simplified picture of the fuel ring main. But in fact, it looks rather less neat and tidy when seen, as it is here, applied to a typical works research unit. This engine is first run on ordinary diesel fuel, and its performance is recorded. The pipework running along the top of the engine is in fact the ring main, which will shortly be carrying not clean diesel fuel, but this specially imported sample of crude oil from the wells at Nahokatia. For the test with crude oil fueling, the engine is started on diesel oil. This time, no prolonged test is made with the conventional fuel, and after a minute or so, a lever is moved, and the ring main starts to feed Nahokatia crude to the engine. Now the engine will run under load for 500 hours, and frequent readings will be taken at the engine and at the generator which it's driving until the great mass of data required has been accumulated. The first performance figures are important to all concerned. It's also important to know just what is going to be left in those ring main filters after 500 hours of running a really big diesel like this on what is, after all, a purely fortuitous mixture of highly volatile petroleum products, something uncommonly like candle grease, and a lavish dash of good old Mother Earth, sand and all. This is where the filters, which later on will have the highly important job of keeping the worst of the foreign bodies out of the engine, do an extra job of showing just exactly what they can trap, and therefore, by implication, what is likely to be offered to the engine as fuel. Dirty enough stuff it looks to the naked eye. But under the microscope, it's hard to believe that any engine would accept it as fuel. That's the sort of fuel the engines will have to use to move 700 miles of waxy, sulky crude. But what sort of engines will they be? Well, first of all, the fuel situation along the pipeline dictates the basic engine design. At Nahokatia, the enormous supply of natural gas, some of which hitherto had been flared off, was to be used as fuel, in conjunction with a small percentage of the crude oil from the same important local wells. Where gas was available, the answer was a dual-fuel engine, one which can run on liquid or gaseous fuel, the gas being ignited by a small amount of liquid fuel. The engine is started, and to begin with, runs on liquid from the pipeline, like every four-stroke diesel. But once it's running on oil, it can be switched over by manual control to run on gas. This changeover does not interrupt the output of power. When running on gas, the consumption of oil is reduced by over 90%, and in the event of a failure in the gas supply, the engine reverts automatically to oil, at the same time closing the main gas valve, which eliminates any possible danger when gas pressure is restored. By now, the contractors out in India are beginning to show results in the work of erecting the pumping stations along the pipeline. For the first time, it's possible to get a more than purely theoretical idea of where everything is going to be put and how it's all going to fit together. For the first time, too, even the most determinedly professional engineer cannot help but catch a whiff of the heady air of creation that is about. For this is going to be more than a big subcontract to a huge undertaking. It's taking part in the explosive emergence of what is a continent in all but name, as a partner in the wonders and responsibilities of the second half of the 20th century. For the pipeline and its pumping stations will be run by Indian engineers, graduates possibly of this very institution in the state from which the crude oil comes. India, like every other state at a critical stage in industrialization, is training her technical students wherever the best in knowledge and technique is available, including the W.H. Allen Works at Bedford, where this group is studying work in the electrical shops where the self-regulating alternators for the North India Pipeline's power supply are being made. No young engineer can get far without a good theoretical training, but nevertheless, first-hand experience of the problems and the skills of the actual builders of modern machinery can do something beyond the power of any textbook. The complex organization of manufacture and testing moves forward all the time, each item being fitted to its appropriate neighbor in the scheme and the scale of operations growing all the time until it culminates in the products of the electrical and the diesel departments being coupled together to run the most important test of all, a pair of newly built engines driving two of the actual alternators under load. This is a test to prove the performance of complete units, but to the layman, it has more than a little of the panache of the concert platform. This full-scale test is in fact the last of any kind that the equipment will undergo before it is started up on its permanent site in India. For this reason, if for no other, it is attended not only by the members of W.H. Allen's team of specialists, but by the engineering representative of the customer. No sooner is the engine shut down than a complete dismantling begins. Everything is stripped down to its component parts and a minute examination is made to discover whether any part has in any way deviated from its expected performance, calculated not only on design theory, but from the earlier practical tests. Here again, the customer's engineer is very much in evidence and becomes a part of the manufacturer's team in their common search for any sign of abnormal wear. For this is common ground, and maker and customer share a common aim, the best that engineering skill can produce. As each section is inspected and passed for export, it has to be prepared to withstand the various hazards of the journey. Of these, heat and damp are not the least, and it's necessary to enclose many of the more delicate parts in airtight polythene bags, carefully sealed, and from which the air is then mechanically exhausted. This method provides very effective protection from extremes of climate. And of course, the relatively delicate polythene is further protected by waterproofed heavy crates from the more violent hazards of long-distance travel. Once again, minute care characterizes even the apparently less enthralling processes of packing, and rightly so. For these crates contain the work of many men and many months, and they have a long, hard journey ahead of them. Eventually, the whole plant, mechanical and electrical, stands crated and anonymous at the assembly point in India. This is perhaps the moment to reflect on how all this machinery is going to work and who is going to work it. The most important part in the whole scheme of control lies in the second part of the question, for this will be the most advanced pipeline in the world, and the pumping stations will be remotely controlled. This represents an enormous advance over earlier control systems, and months of cooperation between the engine designers at W.H. Allen and the communication engineers were needed. The flow in the buried pipeline will be controlled by a dispatcher who can operate any of the stations by means of an extremely sophisticated control system incorporating a VHF radio network. Most of the control is directly electrical, and for the first time in pipeline history avoids cumbersome pneumatic devices. There she is, a little smarter in her new paint than the last time we saw her, coupled up to the huge ram pump and ready to go. Once the ring main section looked obscure and grubby in the test bay. Now everything looks almost unnaturally clean and bright in the hot sunshine. You would hardly recognize our old friends, the conical bottom fuel tanks, in these gleaming monsters in the background, but that's what they are. Nothing dramatic happens when the power is switched on. Nobody really does anything at all, except one man many miles away. And all he does is press a button. And all along the green foothills of the Himalayas, from Assam to Baroni and far Bihar, 700 miles of oil starts slowly to move westward under the power of 51 diesel engines made in Bedford in England by people who know their job.